Okay, so in part two, in part one, we talked about the electromagnetic spectrum, and we talked about the relationship between wavelength, which was the distance between two waves, and frequency, which was how many waves there are per second, and that was related to a constant, which was the speed of light. So now we're going to talk about energy. How do we determine how much energy is in a wave? And remember, energy is basically the ability to perform work. So Max Planck said that energy was not a continuous thing. When we think of energy, for example, when you think of your dining room, you may have a dimmer switch. So you turn it and you can sort of stop it anywhere you want to. You can make that light as dim as you want or as bright as you want, and you can stop it at any point you want to in between. And what Max Planck said was that's not exactly what's really going on. He said that energy was in packets. So think about the difference between a ramp and stair steps. On a ramp, you can take as big a steps or as small steps as you want to, but on a set of stairs, you have to step a certain height to get to the next step, and you can't step in between. So what Planck said was what's really going on in your dining room when you're turning that light up is that it's actually jumping from energy to energy to energy, and you're not actually getting this continuous change. It's just that a quantum, this amount, is such a tiny amount that to you it looks continuous, even though it's not really continuous. And this explains exactly what I said, that it's like stair steps versus a ramp. But a quantum is such a tiny amount of energy, it's not an amount that we would notice. So Einstein related this to light. He said that a photon, he used the word photon, and he said that a photon was a quantum of light energy, specifically light energy. So quantum refers to energy, but a photon refers specifically to electromagnetic energy. So this goes along with something called the photoelectric effect, which basically was discovered when you would shoot a beam of light at a metal. Electrons can be emitted from the metal, and this is how photocells work in a camera. When certain wavelengths of light hit it, this is how you get your image. But anyway, so what would happen is if you shot these photons of light, it wouldn't matter how bright the light was. If, for example, I shot yellow light, which was a wavelength of, let's just say, 500 nanometers. If I shot that at a particular metal, if 500 nanometers was not a wavelength with enough energy, it wouldn't matter if I turned the light up really bright yellow or whether it was dim yellow. That didn't matter. It was the amount of energy in the wavelength. On the other hand, I might take instead, let's say, blue or violet light, which now has a much higher amount of energy, and if I shot that at this same metal, it would trigger an effect. And in class I showed you the beads that responded to UV rays, that you could hit them with just white light from the room and nothing would happen, no matter how bright the light was. But if you put them under ultraviolet, it triggered the phosphor in the beads, and then you could see the color. And we also did a little demonstration where we had this glow-in-the-dark paper, and we had a rainbow of filters, red, orange, yellow, green, blue, and violet, and we held it under a light and then turned out all the lights and looked, and the only two that the actual wavelengths were strong enough to actually stimulate the glow was blue and the violet. So anyway, so this is also how your garage door works. You have infrared, I believe those are usually infrared. They go across to a receiver, and if you break the beam, then the door won't close, and so you don't get smushed. Anyway, so this is the formula for it. Enter the amount of energy that a photon of a particular light will have is equal to Planck's constant, which is, again, a constant, 6.626 times 10 to the negative 34th joule seconds. That's what this is, joule seconds. And so this times frequency, remember this was new, will give you how much energy a photon of a particular light has. So Planck's constant will always be provided for you. And so just like the other formula for the speed of light, you are going to be given one of these things and you'll be asked to solve for the other one. And on the next slide, I believe I have a picture of the photoelectric effect just to show you what it means or what it looks like. Let's see. This is explaining what I had said. Okay, so for example, sodium, red light hitting sodium, no effect. Violet light hits sodium, you get a reaction. And here's sort of a diagram. So here's this is potassium, and you need a particular amount of energy for the electron to get excited. And notice nothing happens with red, but green is strong enough, which means anything beyond green would also be strong enough. It's sort of an all or nothing thing. It would either, the electron would go faster if you hit it with a stronger wavelength or a shorter wavelength of light, but it wouldn't necessarily expel more electrons. So next, okay, so just like before, here's a sample problem. What is the energy of a photon whose frequency is 2.22 times 10 to the 14th seconds to the negative 1? Remember, that's hertz. And so here's our formula, E equals hv. H, remember, is Planck's constant. It's actually not V, it's nu. And so therefore, the amount of energy is going to be equal to 6.63 times 10 to the negative 34th times 2.22 times 10 to the 14th. And that's going to give us an answer. It looks like I didn't work it out. But that'll give us our answer. We will actually round this to 3 significant digits. And now, what is the frequency of a photon whose energy is 6 times 10 to the negative 15th joules? So this time, what you're going to do is you can manipulate this formula. The energy over Planck's constant will give us frequency. And so if we plug that in, it's going to look like this. It's going to be 6 times 10 to the negative 15th divided by, in this case, 6.63 times 10 to the negative 34th. Remember our units here. Okay, so I just went ahead and closed this so you could see the answers. So for this first one, our final answer here was 1.47 times 10 to the negative 19th joules. And I wanted to just show you really quick why it's joules. If you recall, Planck's constant, H, is in joule seconds, and frequency is seconds to the negative 1. That means that when you multiply them together, seconds is going to cancel. You're going to have seconds over seconds, and so our answer would then be in joules. For our second one, this time they're asking for frequency, so we have 6 times 10 to the negative 15th joules. Our energy would have been in joules, and again, Planck's constant would be in joules per second. Or I'm sorry, joule seconds. So that's a joules times seconds. Joules is going to cancel, and you're going to be left with your answer in over seconds, or seconds to the negative 1, or hertz. And again, significant digits. Your original number had 3. Your answer has 3. Here, your original number has 3, so your answer has 3. Don't use, even though in this case they both have 3, don't use Planck's constant to determine where you should round. Okay, this last little segment is not going to be on your test, but I just wanted to make a comment about Louis de Broglie. So de Broglie said light has some properties of matter. We said that light can behave like particles, so he thought if light can behave like matter, maybe matter can also behave like light. So if light can behave as a particle, maybe matter, which is a particle, could behave as a wave. And he actually said that electrons, even though they are particles, might actually behave like light, behave like a wave. And he came up with a formula that basically incorporated mass here into the formula. So he had that wavelength was equal to Planck's constant over mass times frequency. And so he said that the wave characteristics that matter has would be called matter waves. So here's the thing though, even though matter might have wave-like properties, the wavelengths, because matter weighs so much, if it's something really, really big, the mass is going to be much bigger. The bigger the mass, the wavelength is going to be extremely tiny. So even though matter might have wave-like properties, the wavelengths would be so tiny that we wouldn't be able to see them. So we don't measure, traveling matter in waves, but electrons are very tiny, and since the mass of an electron is so small, then we could measure the behavior of an electron as a wave, because the wavelength would be something that's readable. And so that pretty much wraps up the whole first section of this chapter on waves. Please see me if you need help with the math, because obviously it was a little difficult to write out math stuff on this laptop. So if you need help in class, see me.